recording and then. Welcome back, everyone. It is my great pleasure to introduce Dr. Limin, an associate professor, research professor in the Electrical and Computer Engineering Department at CMU. She received her PhD in computer science from Princeton University and her BE in computer science and engineering from the University of Science and Technology in China. She's a member of SciLab, CMU's Computer Security and Privacy Institute, and her research interests are in formal aspects of software security and in particular applying formal logic to constructing software systems with known security guarantees. Thank you for joining us, Limin, and please take it away.
So can you enable screen sharing?
Oh, we haven't made, okay, yeah, I need to make you the host. Here we go.
Yeah,
you should, so co-host, sorry. There we go.
All right.
And you should be able to share your screen now.
All right. You guys see my PowerPoint?
Yes.
All right. Let me see. Let me get a few things ready. It's my pen. Okay. Let me try it with my pen. Okay, it works. All right, so thanks for coming to my talk. I'm going to talk about connecting information flow types to runtime monitors while gradual typing. So there are actually three keywords on this. There's information flow types, there's runtime monitors, and then there's gradual typing. So I'll go through them in this talk, and in the end, I'll try to connect them all together. So this is more of a tutorial style talk. So if you're already in information flow, I hope this is fairly easy for you. If you're not in this, I'm trying to just give you a base knowledge of how things work and talk in the end, very end, talk a little about my work on gradual information flow typing. All right, so I'll start by essentially explaining what's the information flow security via example. This example is based on Strava. So Strava is this exercise app. I have one. When I go out for a run, Strava tells me where did I run, how long did I run, what's my heart rate, what's my speed, and so on. Strava has a lot of users. So Strava generated something called heat map. In the past, this heat map is considered public. The goal is to tell people in one region what are the popular roads people actually cycle on or run on so that you can plan your exercise accordingly. The problem here, this is the headline 3 years ago in Wired. The problem is this heat map in question. So this is a heat map actually of a military base. So you can imagine on military base, the soldiers also exercise, they sync with their Strava. Now the heat map generated for this military base clearly shows where the roads are. You can see there's a circle in the middle. That's actually probably a stadium. And then that essentially reveals the layout of the military base and also the patrol routes. These are actually not considered secret. They're not supposed to be viewable by the public. All right. So this is essentially problem is that the information flow is flowing from secret to public. Sensitive information now actually get leaked. All right. So this is a high-level example. I want to be a little more precise about the goal of information flow security. So the more precisely, there are two main goals. One is to ensure secrecy properties. The other is to ensure something called integrity. So for secrecy, it's easier to understand. It's essentially saying that sensitive data should not be leaked to attackers. In the previous example, the layout or the map of the military base shouldn't be leaked to the public. All right. For integrity, essentially what we're looking for is that we're trying to make sure untrusted entities or attackers cannot influence a trusted process. One example we can think of is if you go browse a website, the code, the JavaScript running on the website should not be able to delete all the files on your computer, right? Only you or the admin, the trusted entity using the computer can do such a thing, all right? For this talk, I'm just going to focus on secrecy. This is a more intuitive way of understanding information flow security, all right? Let me figure out. So, are there any questions? Right. If there are no question, I'm just going to move on.
So remember, you can raise your hands if you have questions, and
I can I'll try to man the. All right.
I'll do that for you, Limin.
Sure. All right. Yeah. So there are no questions. I'm going to move on.
No, we're good to go for now.
Yeah. All right. So So that's like, when we talk about security, there's no absolute security. It's always, what's your goal? What's this property you're trying to enforce? So here we're looking at secrecy and integrity. All right, so go back to my presentation. So we have to actually talk about the information flow security in formal terms. So we need to build a security model for this. For us to do this, one important component is something called secrecy labels. Essentially, it is a way to declare what are my secrets in my system. So you can think of in a general computer system, every data object or every principal that could have access to data should be given a security label. And this label indicates the type of secret data that either data object contains or the principal is allowed to learn. One intuitive example is the clearances used by the government. So you think about the government files, there are, here I just give an example. Let's say there are 3 levels of secrecy. They're top secret, they're public. Basically, the file are classified as being top secret or public. And for the people who may want to access those files are given clearances. You can think of the president and maybe a few of the top officials are given the top secret clearance. And then the employees that have to access the file will be given secret clearance. And you and I or random people work in the government building don't have any clearance, meaning that they are only can only view public files. So that's a secrecy label. That's a kind of a policy specification. As I already explained to you, actually there is a partial order between these secrecy labels. You can think of what is more secret than the other label, right? So in this 3 label example, the order is public, secret, and top secret. So on the right here, I have a little diagram here. It's essentially showing the order relation between them. All right. So when I put these 2 together, what I have is something called a security lattice. This L is a set of security labels in the system. Then you have a partial order with this square subset equal that denotes the partial order. In the picture on the right, that's denoted by the arrow going upward. And then we have operations on labels. So we have the join that compute the least upper bounds. In the example on the right, if I try to take the join of secret and public, that will be secret. All right. The second operation is meet that compute the greatest lower bound. Again, using the example, if I try to compute the meet of secret and public, that will be public. All right. So now I have a way of specifying my security policies. What we're trying to enforce is that a secure system only allow information to flow up the lattice. All right. So to give the example here, if I have secret clearance, the files I can read are files labeled with secret or files labeled with public. I cannot read files that label, right? That's against the flow of information as dictated by the security lattice. All right. Any questions so far? So one thing to mention is that if you take a general security class, you'll probably run into something called a BLP model. That's actually the BLP model is about secrecy, about information flow security. The policy specified there.
We have one question from someone. I have unmuted you, so please go ahead.
Hi, I had a quick question.
Yeah.
Is it possible to store more complicated labels? Maybe you want to store like 2 or 3 in parallel in addition to, say, public secret and top secret?
Yes, so this is a general lattice structure. You can have any label you want to. So if you read literature, there are work on using which principal can read-write files. The set of principal can read-write as a label. Then you have to define your partial order. As long as the partial order makes sense, you're fine. So yes, as long as it makes sense for your system and you can have a proper partial order between the labels, then we're good. It doesn't have to be stick to secret public. I also wouldn't be talking about integrity. So when you control integrity, you have a set of labels talking about integrity. You can put them together, or you can try to have one label, try to talk about both. Typically, people have a pair of labels about secrecy, integrity. So yeah.
Thank you.
All right, other questions?
I think we're good for now.
All right, so let's move on. Let's just go back to the Strava example again. You can think of Strava as a program take a bunch of inputs from the user, generate an output. In this example in question, the output is a heat map. So what's happening is that the data that the Strava takes in are Alice access at location on the base, Bob's access at location, Charlie's location, so on and so forth. These data are secret, but Strava will dump out a heat map that's actually public. If you look at the information flow of the computation of Strava, the information flow actually goes from secret to public, which is actually not allowed by the letters. So therefore, this is a violation. This turned out to be a information leak. One more thing I want to mention on this is that in this example, the problem is not Alice's location. The problem is location on the base. So here, because the data is aggregated, Alice data is aggregated among every other user's data, so it's okay to take Alice access data to aggregate. The problem is the location on the base actually shouldn't be leaked to the heat map. All right, so that's the example side. So let's actually go to programs, because this is we actually want to enforce the security policies on programs. So I have to think about what is a program. So typically, let's just be simple. A program is just something that computes inputs and produce outputs. All right. And here in the information flow setting, we're going to label the inputs and outputs with their secrecy labels. So here, I'm going to abbreviate the letters. From now on, I'm just going to use these 2-point letters that only have 2 labels, L and H. L meaning these are public, H meaning they're secret. So L can flow H, but not the other way around. All right. So if I look at the program, within the program, there are mainly 2 types of information flows that we need to worry about. One type of flow is called explicit flows. So these happen when you do things like assignments. So here, the content of X now move to be stored in Y. So we have an explicit flow from X to Y. All right, that's the first type. The second type is called implicit flows. So this happens when you do a branching. So here I branch on X and then I assign Y different values. So I still have information flow from X to Y because the value of Y is influenced by whether X is positive or not. But this is not assignment. You don't get the precise value of X into Y. Instead, you get some conditions about X into Y. So this is called implicit flows. So typically happen in a branching statement. All right. Any questions so far?
Remember to raise your hands if you have any questions to Limin. Otherwise, it seems we are good to go for now.
All right. So now, given these 2 types of flows, given the example I've shown you, so these 2 programs are safe if the label of X is lower than or equal to the label of Y on the letters, right? So that's following the information flow. However, if the other way around, if the label of X is not lower than or equal to the label of Y, we're going to leak information. All right. So what we're going to talk about for the rest of the talk is try to figure out if I have a program, how do I make sure that I don't leak information given the policies on the inputs and outputs. All right. So all right. So I am going to move on. So we're going to talk about how do I enforce information flow policies. So on the bottom of the diagram, I have this program. Essentially, I draw out all the possible flows. Secret input could be flowed to secret output, which is fine. Secret input, however, cannot flow to public output. That's a flow we're actually trying to get rid of. All right. So in terms of enforcement, there are two main approaches to reject programs that leak information. The first one is a static approach, is using information flow type system. So essentially, I'm trying to use types to specify security policies and use a type system to throw out leaky programs at compile time. All right. The second one is a dynamic approach. I'm going to use runtime monitors to essentially observe how the program runs. If the program is about to do something dangerous, I would stop the program from running and abort the program so that I don't leak information. So these are two main approaches in enforcing information flow policies. So let's start by looking at this information flow type system. So essentially what's going on is that, types essentially specify what this, in theory, types should be specify the correctness property of the program. So now we're looking at security or information flow properties. The correctness we care about are not leaking information. So therefore, we're going to use security types. We're going to label your base types with a security label. Here, we only care about secrecy. So we're going to label the base type with a secrecy label. So here, in the past, I would say X will store integer, Y is also store an integer. Now I'm going to say X store integer. That's actually does not contain any secret. So I have int L as the security type for X. And for Y, I'm saying that Y stores a secret. So Y's type will be int high, indicating that Y stored integer that's considered secret. All right. So this is in line with how we use types. We want to use types to specify important properties of the program. Right. So here for us, the important property is the secrecy level of our data. Now for type systems, so this we have two judgments. So imagine a very simple program. I'm not going to show the syntax. I just show you a few of the typing rules by example. I have expressions and commands. When I type check expressions, in addition to having say the expression E has type tau under gamma, I'm going to say the expression E has type tau with a security label L, and also in gamma for the binding for variables, each variable has a security type that has int L or int high, rather than just having int or bool type in gamma. So here's one example typing rule for sum. So if I want to do the sum of two expressions E1, E2, E1 will have the type int with the label L1, E2 will have the label L2. Now the sum of this, because the sum actually have information flow both from E1 and E2, so I have to compute the join of the two labels. That means that in this simple 2-point lattice scenario, if any of L1 and L2 is high, the resulting label will be high, right? If one part of your addition contains secret, the sum also contains secret as well. All right. So that's expression typing. Any question about this?
There doesn't seem to be any so far.
All right, so let's move on. So next one is about expressions. So notice it's expression typing, sorry, commands. Commands don't really have a type. You always have unit type. So there's no type after C. However, I do have extra components here called program counter. This is essentially indicating to me where this command is executing, what security label is this command executing under a branch. So it's easier to explain when I actually directly show you the branching type checking rule. So here I have a branching statement. I say if B, then C1, else C2. So I first get the type check B. B is a Boolean, and B has a label L. So now I'm going to type check C1 and C2. Remember that we have implicit flows if you branch on a high variable. Basically, this means that we need to remember that when I'm inside the branch, there could be implicit flow from the branching variable to the variable you might assign inside the body of the if statement. So therefore, the program counter's goal is to be here to remember essentially the context where the implicit flow could possibly happen, right? So here, if your original program counter is PC, now when I type check C1, C2, it has to be type checked under a counter that's joined with the label of the branching itself, right? So that's where the program counter comes into play. It's really meant to make sure I can account for implicit flows to make sure that I cannot assign a low variable in a high branch or a high PC context. So that's a rule. Yeah, so that's the if rule. Let's look at the assignments rule. When I have these two rules together, I can give you examples. These two things together. Yeah, there's a question.
Yes, there is a question.
Yeah.
Let me just.
Can you explain what a command is? I didn't get that.
Oh, so expression are pure things like plus, and or negation. Here, commands are just things like branching. This is one command. Assignment is another command. These things have side effect. They modify the store. Yeah.
Okay. Cool.
You could put them all into expressions. Sometimes separating them a little bit cleaner. So here we're just doing the separation here.
Okay.
We have one more question.
Yeah.
Hey, so what prevents these types from being added to more popular languages at this point? What are the kind of obstacles from doing that? I know like Jeeves does something like this.
Yeah, so this is a good question. So the problem is more of a usability side of things. asking programmer to write annotating types is a huge burden. Also, sometimes when system gets complicated, how to design your letters to make sense. So here it's not all the language only have low and high. If every language only have low and high, our life will be so much easier. That can be easily added. But a lot of times to make it work, to make it useful, you actually have to have elaborate letters to think about how things work. I think the burden is the usability side of things rather than theory side of things. So we have lots of good theory here. I think GIF is a good example that in the PL. I think another somewhat good example is actually SE Linux. The way SE Linux manage their access control system have a flavor of information flow a little bit there. If you're interested, you can take a look. But SE Linux, again, got lots of complaints about admins. Nobody wants to use them because they're confused. They have no clue why things doesn't work. So yeah, that's my answer.
Okay.
Yeah, so I think some of you are interested in usability. This is actually one interesting part, like what's the best way to make it usable so that it has wide adoptability.
Thank you.
Yeah. All right. So let's go back to the assignments. So here I'm assigning E to X. So there's obviously an explicit flow from E to X. So I have to look at label of E, look at label of X, make sure that the E's label can flow to X label. So that's the condition up here, right? So that's checking the explicit flow. There's also implicit flow because this assignment could have happened inside a branching. We make sure that now we have to, that's where the second conditions come in. So here we're checking the PC is lower than X label. This should be a subscript. Combined with the two, essentially, if this assignment happened in a branch, the branch label would have been in the taken care of in the PC. As long as I check the PC is lower than equal to X label, I'm taking care of the possible implicit flow in the branches as well. All right. So here is, let's see if I have an example. All right. So here I have one example. So let's just use the gamma to be what I wrote on the left. X is low, Y is high. So when I do an assignment, I'm going to use this rule. Even before looking at PC, I'm comparing whether Y can flow into X, right? So here I'm actually checking, it is a case that H is lower than equal to L. This obviously is not true. So this program actually can type check. This will be ruled out. The explicit flow being ruled out. And then the second one, let's see, my screen now is blocked. All right, move this up. The second one is this if statement. So here the policy that Y is high. So when I'm inside the if, when I try to type check these assignments, I'm under a PC high. So here when I type check this, PC equal to high. However, X label is low. This second condition, when I check it, you'll be trying to check whether H is lower than L again. This again doesn't work. So this is an implicit flow case where the type system again can rule it out. All right. Any other questions about the typing rules?
I think we're okay.
All right. So that's the typing side. So now I'm going to move to the dynamic runtime monitor side. So what the runtime monitor is doing is that it observes program execution. So what I write up here on top of this tuple is the configuration of my program. C is a command to be executed. Sigma is my memory. It's actually mapping variables to its values. Obviously, I have labels associated with them. Then PC is a current program counter I have to remember. So the monitor look at this current configuration. It look at the command that's about to be executed. Here, I'm just going to say make two decisions. One is to say, oh, this is fine. You can go step to the next state. Or the monitor say, no, you cannot do this because you're about to leak information. Now I'm going to abort. So that's the typical two type of decisions a monitor would be able to do. All right. So that's a high level. Now let's look at the monitoring rules again through examples. So I write here is a configuration. So PC is up on top. I'm assuming that I'm executing under a low PC. Here's my store. I have X, Y, Z stored here. Only Y is high. The X and Z are low. And I'm trying to do assignment, trying to assign X to Y. Sorry, assign Y to X. So when this program executes, the monitor essentially asks the same question as the type system. Because there's an explicit flow, the monitor going to ask can Y flow to X, right? I look at Y's label, I look at X label and try to do this comparison. So here it doesn't work. So the monitor is going to say, I'm going to abort the program, I'm going to stop now because you're about to leak information, all right? Here's another example. So this is a simple rule where, again, it's an assignment, but let's assume in this situation, I'm executing this assignment inside a high PC. It's indicated by H here. First thing I'm going to check, because this is a assignment, there's an explicit flow. The first thing I'm going to check is whether Z can flow to X. So I look at label, that's what I need to check. Second, I also need to check whether there's any possible implicit flows. The implicit flow is indexed by whether the PC now can flow into X, right? So this will be asking whether H is lower than L. So the first one is fine. There's no explicit flow because you're assigning low to low, it's fine. But however, the second one is not fine because you are inside a high branch. So you're actually allowing an implicit flow if the monitor were allowed to continue. So after these two checks, the monitor decided, oh no, you cannot continue because there could be a possible bad information flow. So now this program also aborts. All right, any question here?
Nope. Good for
All
now.
right, so let's look at the if branch. So actually, yes, I forgot to mention. So as I was saying, actually there are different designs of the monitor. The way this monitor in the second step just prevent any low assignment in high context is a strategy called NSU, no sensitive upgrades. There are actually other monitor designs do different things, but I'm not going to talk about this here. Essentially, when you have different designs, you are offering different security properties. You're also offering a different trade-off space in terms of performance and overhead and all that. So if you read the literature, there are actually many different kinds of monitor designs, but NSU is one of the better known ones. All right, so I haven't talked about how do you maintain the PC and in the runtime monitor. So in sometimes the configuration is part of your monitor state. So actually I need to keep track of a stack of PCs. So what's happening here is that, again, I'm going to use the example with the if statement. The configuration is that I start with a PC context low, and I'm trying to execute this branching. So actually, when I'm step inside the branch, because Y's label is high, I know that current PC label needs to be joined with the previous PC label, but I'm going to put it on top of the original PC. The reason is that after if statement, there are other commands also. If I don't have the stack, then the other commands after if statement would have to be evaluated under high PC context, which will cause you to rule out a lot of legitimate programs. Therefore, to be more precise, I actually need to keep track of stack of PCs. When I go here, I add a pop to remember that when Z equal to 1 is done, I need to pop the PC stack so that I go back to my original PC level to lower the PC back to where it was. So here, basically, when I do this assignment, obviously, in this case, Z is low, there's an implicit flow. In this example, I'm going to go to abort. If this were to be allowed, I'll go to skip, and then I'll return back to the original low PC level.
Just to say that we have a couple of questions, and Limin,
Yeah.
I'm going to unmute them, chatting.
Yeah.
Can abort be a leak?
Yes,
Like,
abort can be a leak. Yes. So if your program is termination, if you want to enforce a property that's termination sensitive, if the attacker by terminating knowing something, then yes, that's a bit of information leak. If you are aiming for a weaker property, which is termination insensitive, meaning the attacker have no clue that I'm terminated, then you are fine. So yes.
no, but like depending on, you can have information leak, like you can abort on one branch and not abort on the other, right? And then depending on if you abort or not, like you can figure out what the conditional was. Like,
yes. So the property you're talking about is termination sensitive in that the attacker knows that how do I say this? Maybe it's easier when I explain the properties. So when I explain the property, basically, I only ensure, so the weaker property is that I only ensure there's nothing wrong if both terminate in some sense. So in this set of way of you do abort, you actually equating the aborting state to any other state. You just assume that once abort, you're completely fine. It's a weaker property for sure. Yes.
Okay, thank you.
Yeah.
Santiago?
Yeah.
Yes, my question is, what is the advantage of monitoring with respect to type systems? Because in these examples of monitoring, the variables are annotated with their security level. So I'm wondering if you could just use a type system instead of monitoring.
So this is, if your system is very simple, like a simple, you can imagine the language I've been using is pretty simple. You can do a pretty good type system to rule out bad programs. If I'm talking about a real system like JavaScript, there's no way you can have a type system to do all the things you want. Or if you have a system with higher order stores, you actually have a proper, you have to have really good alias analysis to make sure that the effect on the higher order writes and reads are captured properly. It's actually extremely hard to design a good type system people would use. On the other hand, the monitors don't really care. You just throwing a few labels. It just keep monitoring. You don't have to do this alias analysis at the compile time. It makes sense. It's less complexity at the design and also usability level.
Okay, thank you.
Yeah. All right. Other questions?
No, that's it for now. Thank you.
All right. So that's pretty much the monitor rules I'm going to talk about. The next big question is, how do we know our design system is correct, right? For example, type system or the monitor themselves. So for a type system, typically you prove progress and preservation, but here we're trying to enforce a security, information flow security property. So the correctness is slightly different. In addition to progress preservation of your type system, you also want to prove that your type system, the well-typed program, do not leak information to attackers. So let me see how much time. I'm going a bit faster. So this set of properties are typically defined in terms of some way or form of non-interference properties. As I was saying, that they're actually different, there are subtle differences between different statements of non-interference. They're all called non-interference, but the statements actually are different. Some are weaker than others. At the high level, what we're trying to say is that secret should not interfere with public output, or attacker cannot learn any information about the secret by only observing the public outputs. Right, so here we're already assuming that the attacker is someone who has clearance to see the public data in this particular example. More precisely, we say that the program is non-interferent if given any two executions of this program such that the input only differ in secret inputs, the public outputs are always the same. So to show in this little picture, on top on the solid line, I have one execution. On the bottom, the dashed line, I show another execution. So here, the red inputs, these are secret inputs. They may differ in these two executions. This program is non-interferent if the output here, the green output the attacker can see, remain the same. This is saying that the attacker actually cannot guess what the secret value might be, or there's no dependency between the public output and the secret input. All right, so that's a way of specifying non-interference in this very, very simple sense. So this is with the two letters. So we can actually do a simple example here. I have X and Y. Here, X contains secret, Y is public. If I have this implicit flow program here, you can imagine that if I have two rounds, one round where X is greater than 0, the other round where X is, say, equal to 0, you can see that the attacker's observation will be different. In one round, Y would be 1. In the other round, Y would be 0. So this program is not non-interferent. It leaks information. Therefore, your type system or your runtime monitor should actually reject this program. All right. So any question here?
No. Okay.
So this can be generalized to a security lattice. When you generalize to a security lattice, your attacker essentially is someone holding on to a security label. Let's call it LA. It can be any label on the lattice. Your secret will be something that has label that's not allowed to flow into LA, meaning they're not lower than or equal to LA on the lattice. And whatever the attacker can observe, our data have this label L that can flow to LA. And then typically we're going to define equivalences of attacker's observation. We say that two values are low equivalent or equivalent in the eye of the attacker. So we're going to mark the raw values with their label as well. If this label can flow to LA, then these two values have to be the same, has to be the same U. if this label cannot flow to LA, then this can be any value. So that's your equivalent relation. And then this is like instances of a theorem. This is not the full theorem, just to be simple. So if I have a closed expression has type tau with some label L, if I give you two equivalent memories, you can imagine these memories will differ in secret, but are the same in public value. If I execute E in the first memory, give me V1, and the other one give me V2, then the resulting value has to be low equivalent. All right, so this one is called termination insensitive because I require the expression to not term, both of them have to reduce to a value. Only then I need to check the results are equivalent. So you can imagine in the monitor abort case, for me to have a weaker theorem, I'm going to define abort to be equivalent to any value there is. So therefore, I will declare doing the abort will not leak information. But for a stronger theorem, you would have to do better in your monitoring rules. So I'm going to skip the theorem for commands for time's sake, but they're quite similar in the way to specify what ought to be equivalent in the eye of the attacker. So the last bit is actually do the connection, right? There are already questions about why even bother with dynamic, why not fully static. So the reason is that you have legacy code. You also have complex programming languages that you may not be able to fully do things fully statically. So here we can actually connect them using something called gradual typing. So the idea here is that instead of having the programmer specify the policy everywhere, I'm going to have parts of the program to have policies. So for example, here, I can say that X is going to be having a low or high label, but there are other parts of the program, I'm not going to ask programmer to tell me what's the label. Instead, it can be assigned this dynamic label question mark. So E will have, sorry, X will have a tau with question mark label, meaning that I don't know what's the label of X, just do the right thing at runtime. So essentially here, the type system would check all the static parts, rule out bad program. The type system know for sure going to leak information. And then for the question mark, the type system not going to do anything about it. It will just let it go. Instead, we're going to ask the runtime monitor to make sure that at runtime, these question mark labels behave properly. All right. So again, I'm going to try to show an example here. So essentially for me, for this to work, I have to augment my security lattice, the partial order relation. Now I have a new label question mark. So because the type system statically not going to do much about the question mark. So I'm going to allow the question mark to be both lower or equal than all the labels, and also allow all the labels to be lower than or equal to the question mark. So the type system will let the question mark go. So in this example here, I'm doing a branching on X is high, then I'm going to assign Y. Here, because Y is question mark, the type system just say, oh, it's fine. I'm not going to do anything now. However, if this L were to be low, marked here, and then the type system would actually rule out this program, because the question mark type system would defer the, I guess, checking, making sure Y is okay at runtime.
Limin, if it's okay with you, we have one more question.
Yeah, sure.
Please go ahead.
This is a bit unrelated, but in what situations does information flow tracking break down or isn't very helpful? Like maybe in privilege escalation, perhaps?
What's the last sentence? Sorry, I didn't get the last sentence.
What
Like,
situations does
breaking down
information
your
flow tracking break down and or isn't as helpful in enforcing these properties?
That's a good question. One common scenario it breaks down is when you have declassification. So actually the heat map example, I'm actually declassifying because the location information contain Alice and Bob's personal information, also contain the location of the, of that location, sorry, the coordinate of location of military base themselves. So when you put all data together, the problem is not Alice and Bob data goes in. The problem is the base coordinate goes in. Well, we're actually declassifying this information, saying that, oh, it's okay to be Alice and Bob's information because we're computing aggregates. It's totally fine, right? So when we go to declassification, that's the tricky part in terms of doing information flow tracking. Both the type system has to have good ways to handle this until runtime as well. There's work in there, but this is kind of the constant battle in information flow security. How do you make the classification work properly, also enforce the correct properties?
Okay.
Yeah. All right, so for me to look at runtime semantics, I first have to answer the question of what the question mark label means. There are actually many different interpretations. Even within my group, we have 2 different papers on this. But for the sake of this talk, I'm going to take the interpretation that the question mark actually indicate that there is a possible set of labels that could be assigned to this variable. So here, because we're working with the lattice, this is going to be an interval of labels on the lattice. This is in line with one of the earlier POPL papers about abstract gradual typing, where you interpret question mark type as possible types that does not violate preservation. So this is kind of what we're trying to go for as well. So this means that runtime, what the runtime monitor is doing is, once the runtime monitor sees a question mark, it's trying to remember what's the possible interval of this question mark. If it's up to a point where this interval doesn't make sense anymore, this program needs to abort. So here's the example. Again, I have X and Y. Because the interpretation of question mark, now everything, instead of having label, we're going to label it with the possible intervals, because X is high, so the possible interval is only between high and high. Y, however, is question mark. Given our little 2-point lattice, initially Y's label can be of the entire range between low and high. So when the monitor runs, when I'm in this if branching, the first thing I do is to up the PC label to be high, because I'm branching on high. And now when I'm doing these assignments, the runtime monitor will not abort, because this is fine, because the possible labels of Y is a range. Now what the monitor does is actually refine these labels, saying that I know that now Y is being assigned under a high context. Therefore, I need to remember that I have to refine the Y's label to make sure that now Y can only be high. It cannot possibly be low beyond this point. So basically, in the gradual typing, you can imagine that if how do I say this? If at some point Y's label were refined to be low and low in this case, this assignment would have aborted. The monitor would know that now it's not possible to move from this point onward, because we're inducing a implicit leak here. So that's like a simple example. Any question here? There are actually a lot of nuances in terms of design of this monitor itself.
There doesn't seem to be any questions so far. Thanks.
All right, so I think I'm about to finish. So just last bit. I'm in this gradual type system. So in addition to progress preservation, non-interference, there are also other meta properties. As the meta theory is interesting. These are gradual guarantees. So there's a static one, there's a dynamic one. It's basically saying that if you have a program that's type checked with a precise type, then if I remove some of the types, turn them into question marks, this would also type check. There's a corresponding one with a dynamic. This is interesting because this is saying that if the program is being lazy, as long as this program is typable or can run without error, then we shouldn't penalize the programmers for being lazy, not marking the types. Our type system and the runtime combined together should be smart enough not to reject these programs. All right. So on the bottom is just an example of what's more precise, what's less precise. So here, Y's type on the left is concrete, so it's more precise. On the right is a question mark, so it's less precise. So that's where the preciseness definition, roughly how it goes. So, okay, so this is actually the end of the talk. What we're talking about is saying that essentially briefly introduce what information flow security is about. We're trying to prevent information leakage, also integrity violations. For this talk, we mostly focus on information leakage here. We look at enforcement mechanisms. The 2 main categories are type system. The other one is runtime monitors. So each one of them actually, in terms of work, there are many different designs, both within the type system, also within the runtime monitor. And now what's interesting to me is that if you look at gradual typing, it's actually a bridge connecting these 2 worlds, because there are so many designs in type system, there are so many designs in runtime monitors. Actually, how the bridge connect, this actually become, again, a design question. What kind of gradual typing, how do you do the both the static type and also dynamic type, so that I can go from different type system connect to different kind of runtime monitors. So here, I only showed one design, but this is a wide design space that I'm interested in exploring further. So these are the most relevant papers that I mentioned in this talk. And if you're interested, you can email me, I can give you more references. All right, I'm here ready to take more questions.
Thank you so much, Limin, for a fascinating talk. Thanks a lot. I personally learned so much. If there are any questions, please do raise your hand. But a lot of you, yes, Yatin, you're already unmuted. Please go ahead.
You mentioned that the benefit of gradual typing is that the programmer doesn't have to specify types. Can you explain why type inference is difficult here?
So gradual typing is different from type inference in that when you inference a type, let me say, okay, I don't have a good example. There are actually programs you cannot statically type, but at runtime you can use a monitor to make it safe. I don't have a good example off the top of my head.
Okay.
Yeah, so there is a space where you cannot inference a principal type to make it type check. But if I run it, if I monitor it at runtime, it's totally okay, not leaking information.
Right. Yeah, I can imagine.
Yeah.
Okay. Thanks.
Any other questions for Limin? She was kind enough to take lots of questions during the talk, so I think all questions are answered. And in the interest of time, in order to keep to our allotted schedule, so let's thank Limin again and move on to our next talk. Thank you so much, Limin.
Nice talking to you guys. Bye.
Okay. So our next speaker, who is here, Aaron, could you do a mic check with us?
Yes, can you hear me okay?
Yes, all good. Thank you so much for joining us. Let me stop this